So f of x is equal to sin x at x equal to pi by 2. And so this is a continuous at pi by 2. Sin x is a continuous function because left hand limit, right hand limit is equal to the function value at that point. All are equal to 1. Whereas we discussed this modulus x by x, it is discontinuous because left hand limit at 0 is -1. The right hand limit at 0 is +1. Function value is 0. So that's a concept of continuity. Now let's look at the concept of differentiability. We did a few problems on continuity. Let's look at differentiability. From here, the concept of derivative comes into existence. Generally, we memorize derivative formula, but how they are derived, we need to check. We need to understand the basics thoroughly. So, differentiability. So, differentiability at a point differentiability of a function at a point. So let's consider so, yes, let's so let this be x-axis and y-axis. Now let this be a curve, some curve. Okay. Now so let us consider say a point A. This is the function y equal to f of x. There's a function, there's a curve. Now this is the point A. So now let us mark this point with capital A, and then let us take two adjacent points at a distance of A minus h and A plus h from A. Okay. Now let this point be B and let this point be C. So now let us draw. So A, coordinates of A will be A comma f of A, coordinates of this point. On the x-axis, this point is A, and function value at A will be this value. So this is A comma function value at A. All right. Now h is a small quantity, so this is minus h, this is plus h. This is a minus h comma f of a minus h b. C will be a plus h comma f of a plus h. Okay. Now C is a, b, and c. Now let us join the points b and a and draw a chord. Okay, so I have drawn a chord. So AB. So now when you extend this chord, this is called as the secant. This is called as the secant. Now let us draw another chord with another color. Okay. Joining A and C. All right. So this is A. Uh, this is secant AC. All right. Chord. If you join 2 points with a line segment, it will be called as a chord. And if you join, if you extend that line segment, both sides, it is called as the secant. So now slope of AB, secant AB, is equal to AB. So you get y2 minus y1 by x2 minus x1, that form when we do, or so we can write this as f of a minus h minus f of a upon a minus h minus a, which is f of a minus h minus f of a by minus h. This is slope of the secant AB. What is the slope of secant AC? AC. So you get f of a plus h minus f of a by a plus h minus a. So you get f of a plus h minus f of a upon h. Okay. So now what we'll do, these are uh, now we'll make h tends to 0. If h tends to 0, that means this difference tends to 0, then what happens, this point B moves towards A, and because h tends to 0, this point C moves towards A. Correct? So as h tends to 0, B tends to A, point B, and C tends to A. So this limit, now limit h tends to 0 of slope of secant AB is limit h tends to 0 f of a minus h minus f of a upon minus h. Okay, this one, slope of secant AB. This is, what is this? Now as B tends to A, that means B coincides with A. All right, then what happens is this. I'm drawing this green line. You observe this carefully. This maroon line becomes this green line. Understand? It
Sir,
keeps. Uh, yes. Yes. Tell me.
excuse me, sir, am I audible?
Yes. Tell me. You're audible. Please speak.
Nothing, sir. It wasn't audible. Your voice wasn't audible, so I
Okay.
loaded
Okay.
on myself and asked it.
Okay. Am I audible now?
Yes, sir. Yes, sir.
Hmm. Now you observe this. So initially this was the slope of this line AB. Now as B tends to A, this point B almost coincides with A, but B is on the left of A. So you get this as the slope of the tangent. Now this line becomes the tangent. So as h tends to 0, very important, this slope is the slope of the tangent at A. So tangent is a line that, you know, touches the curve at one point. That is what is the very raw definition. But actually, tangent is the limiting point of a secant when one point moves towards the other point. So there's the slope of the tangent at A. Okay, which is the limiting position of the secant drawn to the left of A. Now this limiting point h tends to 0, f of a minus h minus f of a by minus h is called as the left hand derivative. This is called as the left hand derivative at a. Left hand derivative at a. Next, so this is when b tends to a. Now when c tends to a, what's happening? Limit h tending to 0, slope of secant AC, which is limit h tending to 0, f of a plus h minus f of a by h. Now this, what happens when c moves towards a? When c moves towards a, c moves towards a. Now this orange colored line coincides again with this green line. Okay, so we call this as the slope of the tangent at a slope of the tangent at a, which is the limiting position of the secant drawn to the right of a. Limiting position of the secant drawn to the right of a. All right, so this is left and this is right. Uh, so this is called as, so this limit h tending to 0,
Right hand derivative.
f of a plus h minus f of a by h is called as the right hand derivative. Right hand derivative of f of x at a. Now, so the function f of x is said to be differentiable function f of x is said to be differentiable at x equal to a if the left hand derivative at a is equal to the right hand derivative at x equal to. This implies limit h tending to 0, f of a minus h minus f of a by minus h is equal to limit h tending to 0, f of a plus h minus f of a by h. So a function is said to be differentiable when these two limits are equal. What are these two limits? Take the slope of the secant from the point at which you need to find the derivative to the left and to the right, and make those slopes approach Sorry for the distraction. So function is said to be differentiable when left hand derivative is equal to the right hand derivative. So what does this mean at geometrically? Geometrically, this means that the curve y equal to f of x at x equal to a has a unique tangent. Unique tangent um, when the tangent is drawn through a secant either to the left of a comma f of a or to the right. So you get a unique tangent whether you take the secant from both sides. Uh, I should say graphically, not geometrically. I'm sorry. This is graphically. This means that the curve is smooth. This curve is smooth without um, curve is smooth at x equal to a without any gaps or sharp corners. Sharp corners or edges. This means that the curve is smooth at x equal to a without any gaps or sharp corners or edges. So now I will give example. So essentially when you say derivative, just by looking at the curve, you can tell whether the function is differentiable at that point. So if the curve is changing its slope of the tangent very smoothly, continuously like this, then it is differentiable. But let us say this is a curve and then the curve twists like this. Now when you now look at this point, this is like a sharp corner. Now at this point, if we draw a tangent using a secant to the left, this is the um, tangent to the left, and then you draw a tangent from the right. Okay, I'm using the orange only. These two tangents do not coincide. These two tangents do not coincide. This is mm, tangent from the left or tangent at the right of it. Okay, So then whenever you get a sharp corner like that, it means that the function is not differentiable. Otherwise it is. And derivative, sorry, derivative essentially means it is the slope. It is derivative means it is the slope of the tangent at that point. So let us plot. Let us take an example. Let's take this example. Mhm. Okay, by now you should be able to tell what is this curve. What curve is this?
So modulus function.
Yes, very good. So this is y is equal to f of x is equal to modulus of x. So now we want to find, you here you see in the uh, at the origin there is an abrupt change in slope. You have a sharp corner. Just by seeing this, you can say that function is not differentiable at this point. But in any case, we will do the left hand derivative and right hand derivative. So left hand derivative means I take this point 0 and I take another point just to the left of this point. I take this point 0. So limit h tending to 0, limit h tending to 0, uh, f of, now I am finding at 0, right? So 0 minus h minus f of 0 upon minus h. So this is limit. By the way, I didn't give the notation. The left hand derivative can be written like this: f dash 0 minus, or f dash a minus. That means derivative, left hand derivative at a. So this is f dash 0 minus, that is left hand derivative, is limit f, limit h tends to 0, f of 0 minus h minus f of 0 by minus h. This is modulus of 0 minus h, that is minus h, minus modulus of 0 by minus h. Now h is a positive quantity. H is just a distance, that's right. 0 minus h and 0 plus h, right? So this minus h is a negative quantity, and modulus of a negative number is minus of that number, because modulus will always have to be positive. And this is 0. Modulus of 0 is 0 divided by minus h. So in the numerator, you get plus h. In the denominator, you get minus h. So numerator over the denominator is minus h, minus 1. So this is minus 1. As h tends to 0, the left hand derivative is minus 1. Now look at the right hand derivative. We will write this as f dash of 0 plus. This is right hand derivative limit h tending to 0, f of 0 plus h minus f of 0 by h. So this is limit h tending to 0, modulus of 0 plus h minus modulus of 0 by h. So this is limit h tending to 0. Modulus of h is h by h. So limit h tends to 0 of a constant 1. So you get plus 1. So left hand derivative f dash of 0 minus is minus 1. Right hand derivative is plus 1. So left hand derivative is not equal to the right hand derivative. Therefore, y equal to f of x, which is equal to mod x, is not differentiable. It is not differentiable or not derivable. See the terms, either differentiable or derivable at
Sir,
x
why
equal to
is
0.
it called mod X graph, sir?
Uh, yes, this is mod x graph.
No, sir. Why it is called mod X graph, sir?
No,
I mean, how?
function is mod x, function is modulus of x. So its graph is like this, modulus function. At 0, it's a sharp corner, therefore it is not derivable. Now we know that this line is y equal to x line, and this line is y equal to minus x line. We know this line slope is minus 1, this line slope is plus 1. Okay, from coordinate geometry. Now, so what is left hand derivative? You just see, take the point 0 and take a point on the curve just to the left of 0. So just to the left of 0, you take a point and draw a line, tangent. So here the tangent coincides with the curve. It is not a curve as such, it is a line. Okay, so this is the left hand derivative. Then take the point 0 and take a point just to the right of 0. 0 and point just to the right of 0 on the curve, and then draw a line. That will be your, that slope of that tangent will be your right hand derivative. So here the left hand derivative is minus 1, right hand derivative is plus 1. So with practice, say for me, with, or anybody, if you are practiced, you just see this graph and you can straight away tell what is the left hand derivative at 0, right hand derivative of 0. Left hand derivative at 0 is minus 1, right hand derivative of at 0 is plus 1. If you understand what is derivative clearly, then you will be able to do this. Okay, so this is what differentiability is. That's all. This is just a matter of a curve being smooth or curve having rough, uh, sharp turns or sharp corners. If it's sharp turns or sharp corners, it is not differentiable, and if it is smooth curve and smooth transition, it is differentiable. Next is derivative or differential coefficient at a point. This concept, this is the same. When a function is differentiable at a point, we call that, okay, I'll write this here. If a function is differentiable at a point A, then f dash A is equal to f dash of A minus left hand derivative is f dash of A plus. Left hand derivative, right hand derivative at A. Okay, f dash A and f dash A minus f dash A plus. So this is called as the derivative or differential coefficient. So this f dash A is called as the derivative or differential coefficient of the function y equal to f of x at x equal to a. Now this is also denoted as, now this f dash a also denoted as or denoted by capital D of f at a, or d by dx, d by dx. We say derivative with respect to x, d by dx of f of x at x equal to a, or so we simply write dy by dx, dy by dx at x equal to a. So these are the various notations for derivatives. The most common one is f dash and d by dx or dy by dx. These are the most common and interchangeable definitions. Okay. Now, differentiability on a set of points. So for every, so differentiability on a set, one second. So this is the third point in derivatives. So far we discussed derivative at a point, and then what do you mean by a differential coefficient? We just defined this. We just did one example to show how a function is not differentiable. Now let's say we first discussed differentiability at a point. Now we are discussing differentiability in a set. A function f of x is differentiable on closed interval ab if it is differentiable, first point, at each point in open interval ab then it is then right hand derivative at a, the endpoint, exists. All right, or defined. Next, and the left hand derivative at x equal to b exists. And in fact, uh, right thing is it's exists and finite. So a function f is said to be now. So this one is set. Now a function is said to be a differentiable function. A function is said to be a differentiable function in its domain. No, it's a differentiable function if it is differentiable at every point in its domain. So if it's differentiable at any point, every point where it is defined, then it is called as a differentiable function. Okay. So uh, now relationship, we have done this. Two more concepts, small concepts. Relationship between continuity and differentiability. So you can say for charging a bit, for a function to be differentiable at a point, the following conditions must be satisfied. Must. Okay. One, the function must be defined at that point. If it is not even defined, yeah, there is no point in discussing about the differentiability at that point. Second, the function must be continuous at that point. That means there should not be any break in the graph. The function must be continuous at that point. Third one, of course, after these two are satisfied, left hand derivative is equal to right hand derivative at x equal to a. These three conditions must be satisfied. So, so, so which automatically means you know, so a differentiable function is necessarily continuous. Okay, all right. Differentiability implies continuity. However, continuity does not ensure differentiability. So continuity does not automatically imply
Sir,
different
scroll.
differentiability. Okay, just like we did the modulus of x graph. All right, when we did the modulus of x graph, it's a continuous function. Mod function is a continuous function. The you can draw this mod x graph without lifting your pen. There's no break. So continuously you can draw without having to lift the pen off the paper. However, it has a sharp corner. So here is the example where function is continuous but not differentiable. But if a function is differentiable, it automatically implies that it is continuous. Okay. So, uh, done. Now we'll go to the concept of derivatives. I'll just introduce that and then we'll stop. Um, I'll just introduce that first. Now, some standard differentiable functions.
Sir, the next condition for continuity not equal to differentiability. What is the statement above, sir?
Continuity does not ensure differentiability.
Okay, sir. Okay, sir.
So continuity need not imply differentiability. That okay? It's implied. So interval of differentiability, differentiability or derivability. First is polynomial. It is interval of differentiability is R. Second, exponential. Exponential function is also differentiable on R. Any polynomial, algebraic polynomial, it's a differentiable function. Then constant function is differentiable on R. Logarithmic function is differentiable on its domain. So throughout, and this is a for all x belonging to the domain. Then trigonometric functions. It is all x belonging to the domain. All trigonometric functions are smooth, like tan x is not defined at pi by 2, so you cannot call differentiability at that point. But other than that, all other points it is, wherever it is defined, it is differentiable. So trigonometric functions are differentiable and inverse trigonometric functions are also differentiable. All have smooth curves. They are differentiable for all x belonging to the domain. Okay. So they are very complicated problems also on differentiability. This is a place where students fumble because they don't understand the basic concepts properly and therefore they cannot apply themselves in the problems. Next, the last part for today. Last part, I'll just introduce derivative of a function. Derivative of a function. So let a function f of x be defined on domain D. Okay, on domain D, and be it differentiable for all x belonging to the domain. Now I don't want to find the derivative. Say f dash a means the slope of the tangent at a. Okay, as h tends to 0, f of a plus h minus f of a by h. Left hand limit is equal to the right hand limit. So, but I take the right hand limit. If I take the left hand limit also, it doesn't make a difference. Left hand, this limit h tending to 0, f of a minus h minus f of a by minus h. Either I can take that or this. Now, this is at a point a on the curve, at a point x equal to a on the curve, you find the derivative. That is the slope. Derivative again is the slope of the tangent at that point. So slope of this line tangent at that point a is the derivative. Now I want to find derivative at any point x. So very simple, replace. So derivative of f of x at any point x, any arbitrary point x. So that itself is a function. Instead of a, replace x. Limit h tends to 0, f of x plus h minus f of x upon h. This is the derivative. As long as the function is differentiable, this is the derivative of this function. So tomorrow we will start from here. We'll start our okay. Tomorrow I'm thinking we'll continue on this topic, differentiability and derivatives. I'll introduce all derivatives and then some problems on differentiability, some problems on derivatives. For CBSE students, we'll have a little extended hour on Sunday, okay, on conics.
Okay, sir.
All right. So tomorrow we'll continue this. We'll introduce derivatives. Uh, Actually, derivative of sin x, derivative of tan x, all those important relations. I'll give a full list of derivatives. Okay, we'll stop here for today.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.